Here we have a question on nuclear physics. Let's begin. Radioactive uranium with the atomic mass 238 and atomic number 92 produces a series of decays ending with stable nuclei of lead. The nuclei in this series decay by either alpha or beta minus processes. So here the prerequisite before we continue solving with the question is to remember that when an unstable radioactive nucleus undergoes alpha decay, its atomic mass reduces by 4 and its atomic number reduces by 2. Whereas when the same radioactive nucleus undergoes beta minus decay, its atomic mass remains the same, or it decreases or increases by 0, and its atomic number increases by 1 because it releases an electron with a proton. Let's take a look at the first question. Uranium-238 decays into a nuclide of thorium with the atomic mass 234. Write down the complete equation for this radioactive decay. Looking into the question further, we understand that the nucleus reduces its atomic mass by 4, which means the decay that is occurring must be an alpha decay. Since it's an alpha decay, we understand that uranium decays into thorium with the symbol TH, where it is assumed to be losing its atomic mass by 4, giving the value 234, and its atomic number reduces by 2, giving the number 90, and it releases an equivalent alpha particle which contains the missing atomic mass 4 and the atomic number, that is 2. This is an example of an alpha decay in process. Moving on to part B. Here we have thallium with its atomic mass 206 and atomic number 81, which decays into lead with its atomic mass remaining the same as 206, while its atomic number increases by 1. Here we also understand that the decay that is occurring is a beta decay, specifically a beta minus decay, which indicates that the particles emitted are an electron and its anti-neutrino. To write the reaction, we can write out the reaction as TL with its atomic mass 206, atomic number 81, decays into lead, which is plumbum, Pb, with the atomic mass remaining the same as 206, while it increases its atomic number by 1, because a proton is released, along with releasing an electron, which has the atomic mass 0 and the atomic number -1, plus its anti-neutrino. Here, they have asked us to identify the quark changes of this decay. Here we understand that a neutron gets converted into a proton plus an electron. The neutron is made up of 3 quarks, that is the up quark, the down quark, and the down quark, while the proton is made up of the up and another up quark and then a down quark. So looking at this transition, we understand that in terms of quark changes, a down quark is changing into an up quark for this specific reaction. Moving on to part C, the half-life of uranium-238 is about 4.5 to 10 to the power of 9 years. The half-life of thallium is about 4.2 minutes. Compare and contrast the methods to measure these half-lives. Here we notice, based on pure judgment, that uranium has a very high half-life, whereas thallium has a very small half-life. By comparison, the value of half-life of uranium is improbable to calculate in actual time. Hence, what we could do is, to calculate the half-life of uranium, we could measure the number of radioactive nuclei radioactive nuclei . and measure that against the radioactive nuclei which have already decayed. That is the decayed nuclei. To get a sense of the percentage of radioactive nuclei that have decayed into a much more stable nuclei over a certain course of time. And by measuring this and using the nuclear decay equation, n is equal to n naught e to the power of minus lambda t, where n is initial number of radioactive nuclei, is the initial number of radioactive nuclei, n is the number of radioactive nuclei remaining after a time instant t, and lambda being the decay constant. We can use this to further measure the half-life through the equation. Half-life T half is equivalent to 0.693 divided by the decay constant lambda. To measure the half-life of thallium, which is, when compared to uranium, a much smaller value, in fact, infinitesimally small value, we can just calculate by calculating the activity of thallium over certain instance of time, and by drawing the decay curve, which measures the amount of activity either denoted by A or R and time. And by measuring this, we get to know the half-life of thallium. Let's move on to the next part. Here in the next part, we look at that a graph shows the variation with the nuclear number A of binding energy per nucleon. So here we have a binding energy curve, which is a graph plotted in terms of binding energy per nucleon on the y-axis and nuclear number A on the x-axis, outlined by high temperature is required for fusion to occur. Here we notice that the lighter nuclei have a higher binding energy per nucleon, and we also notice that nuclear fusion is a reaction where two lighter nuclei combine to form a heavier nucleus. A simple example of this could be the combination of a deuterium with a tritium nucleus to give a helium nucleus, along with the emission of a neutron. Here we understand that a high temperature is initially required for the fusion to occur. This is specifically because the energy required to overcome the electrostatic repulsive forces, and the strong and weak nuclear forces within the two nuclei are very high. And this is particularly the reason why a very high temperature is required to overcome these repulsive forces and help achieve nuclear fusion. Moving on to part 2, outline with reference to the graph why energy is released both in fusion and fission reactions. We could straightforward indicate that the energy being released in both nuclear fusion and fission reactions is particularly because the specific binding energy, or also known as the binding energy per nucleon, increases in the resultant side or the product side of the nuclear fusion and the nuclear fission reactions. Moving on to the next part. The last part states uranium-235 is used as nuclear fuel. The fusion of uranium-235 can produce krypton and barium, determined in MeV using the graph, the energy released by this fission. We understand that the binding energy is calculated by the equation total binding energy for a particular nucleus is equivalent to the binding energy per nucleon multiplied by the atomic mass of the particular nucleus, which is denoted by A. We notice that uranium has an atomic mass of 235, which is multiplied by its approximate binding energy per nucleon value, which resides or which turns out to be approximately 7.6. And we subtract this from the combined binding energy of the two resultants, the two products of the reaction, that is krypton and barium. Krypton has the atomic mass of 89 and its corresponding binding energy per nucleon approximately turns out, krypton lies somewhere here, and its approximate value turns out to be about 8.6. And the last element, that is barium, with the atomic mass of 144, has its approximate value of binding energy per nucleon to be approximated to 8.2 on the graph. Simplifying this, we get the energy released, obviously in terms of mega electron volts, because that is what the graph is plotted for, to be equivalent to 160 mega electron volt. So the energy released during this reaction is 160 mega electron volt.